few minutes. So yeah, thanks for coming. I'd like to thank Catherine for inviting me, because she's unfortunately not here, but she can always watch the video if she likes. Yeah, so this talk is a little bit sort of outside of what you might have seen. I have to say a little bit about my background. My background is I'm a numerical analyst, particularly working on numerical linear algebra, but I've started to look into more stochastic problems, which you'll see in this talk. There's a joint work with a colleague from the WIAS Institute in Berlin. Right, so I realize there's lots of statisticians here, there's lots of people who are not familiar with the area. You might recognize model order reduction, but you might not know what balanced model order reduction is. What is Lévy noise, and what's my motivation for this? So I'm gonna be quite slow. Also, I realized I have 2 hours. I'm not going to talk for 2 hours. I was actually quite shocked it's 2 hours, because I don't think I could talk for 2 hours. I don't think you want to.
It's not a challenge.
But if you ask a lot of questions, then maybe we get to 2 hours. So I encourage you to ask questions if there are any questions. So here's my motivation slide, which I'm trying to sort of explain why model order reduction. So I'm coming from the point of view where we have a physical system, and we're trying to model it using PDEs. Obviously, everywhere when there is an arrow, there is error, right? So when you model the physical system with a PDE, you make an error. You discretize it, getting an ODE, you do an error. And this ODE system could be, if you discretize very finely, it could be a very large system. And the idea is that you want to use this ODE to do some optimization, some simulation, some prediction, to control a process. So this is very expensive to solve. But you have often a very limited time to do this solve. So I became interested in model order reduction when I worked on data assimilation, and you have, in a data assimilation where you have a model and data and trying to fit it, you have a very restricted time to do your solve. You only have 6 hours to do the forecast, and that's it. So you want to do this optimization process behind very quickly. So the idea is you have this ODE, you do some model order reduction, so you have a reduced system of ODEs, and you can use that to simulate and control. So you get from a very expensive system to a hopefully less expensive system. And you want to make sure, well, to do all these errors here, that you're still representing the physical system well enough. Although we are actually only looking at the error between the reduced system and the ODE that you have. Okay, here I put like plus data. There are currently no data in my talk, but what you would normally have is also, you have this physical system, you're trying to match it to some data and do data assimilation, but I have currently no data, so to disappoint the statisticians in this talk, but hopefully you can still take something away from that. Right, so here I decided before talking about the stochastic system, because this is the idea comes from a deterministic system. I decided to talk a little bit about that as well, just because some of you might be new to this idea. So I have a linear system, a linear time invariant system. So it's a very simplified problem. So you could think of this as the heat equation, maybe. You have some input, so you have a time-dependent heat equation, so the heat in this room, distribution of heat in this room, and you also have an output. So you're interested in only in the heat in a certain area of the room, maybe, so or a certain function of the heat. So you could think of it. You might be only interested in the temperature here where I'm standing. So an input and an output, and this is the state. The state can be very large. So the system matrix here, or an operator, discretized PDE operator is very large. So your input, your state vector is x. You have an initial condition at time t0, and you have a control u, or an input vector. Could be a heating and a heat source in the room.
Can I just start? So
yeah.
It's worth pointing out that it's time invariant because A, B, and C are fixed and don't depend on time.
Yes, yeah, that's right. And there are ideas for extending this with time variant systems, but things get more complicated now. I decided to keep it as simple as possible. Yeah. And obviously the system is linear, which is also a very big restriction. So I really want to do this for nonlinear systems. And y is the output. Yeah, here's a couple of applications. I said a lot of these things already. So this arises for biological, chemical networks, power systems, electrical engineering, numerical mechanics, etc. Anyway, you've got an input and an output, and you're interested in the output. So you might, might not want to solve this PDE for the whole space. You might just be interested in a certain output and a certain function of the state vector. So this function C, the C could also be a nonlinear function. Okay, and you want to use this so this is very expensive to solve in general. If X is very large, but you're trying to do some simulation or optimization and forecast, so you have to solve this many times. So it's expensive. So yeah, in modern applications, this n could be really large, and 10 to the 6, but really even much higher, and you don't have literally the time to solve this. So I'm assuming you really don't have the time to solve this. If you have an infinite amount of time, you could just solve this and compute the output, but really I want to have a very restricted time to solve this. And this setting appears in many applications. It's written very general, but it appears in many applications. So what you would like to do, you have this large system and you're trying to reduce this. And for a linear system, this is quite sort of easy to do. So you're trying to replace your state x by a state x tilde. And then you have an a tilde, a b tilde, and a c tilde. They're reduced systems. So a is now r by r, where r is much smaller than n. So I'm talking about like several orders of magnitude smaller. Then obviously B and C have to also match these dimensions to work it out. So B is an R by M matrix, C is an P by R matrix, etc. And then the output, Y tilde, is obviously not the same as Y, but you're trying to do this in a way that makes sure that the original output that you have is very close to your reduced output. Because otherwise this is a thing that you would do and without much theory behind it. So you really want to make sure your error is measurable in some sense. Obviously, to get back to what the discussion was last week, I'm starting from a physical system. This system has already a lot of errors, right? So, but I'm assuming that this is the correct output, and I'm measuring the error between this one and the reduced one. But there is a lot of error that you're already modeling the system. Okay, what is balanced truncation? So this comes from there's a lot of model order reduction techniques. This is one that comes from the control theoretic background, so some of you might be familiar with it. I'm explaining it hopefully in detail, so I realize there's not many people probably know much control theory, and if, then please apologies for me. There are many other reduced order techniques. I'm just looking at this one. Okay, so the idea is you do a projection. So you have your large state vector of dimension n, and you project it onto a smaller dimensional space. So you have V as a orthogonal matrix, or just a matrix which is an n by r matrix. There's a long, short, thin, skinny matrix. R is much less than n, and then you just write your system in this form. So you make an error here. That's why there's an approximation. And Y tilde is then obviously also not the same as Y. And then you impose a Petrov-Galerkin condition. You say, okay, you have a matrix W, such that W transpose B is the identity matrix, and you look at the residual here and impose orthogonality. W transpose times this, which is the residual of this system, is equal to 0. Okay, so Petrov-Galerkin condition. And then if you write this out, W transpose V is the identity. Here you get a projected matrix A and a projected matrix B. And for the second equation, you just copy what is up there. So you have a reduced system. Okay, it's a very simple idea. The problem is, there's several problems for doing this. First of all, you want to reduce it in a way that y tilde is close to y, as I said, but also how do you find these V and W matrices, right? What do you do? There's several ways of doing this. One is balanced truncation. Okay, so for that you need to this is where a little bit of control theory comes in. So if you look at this equation up here, you can actually, it's probably sort of undergraduate mathematics, for u equals 0, so if you have no input, you can compute the solution to the system, and you can also compute the output. So y is just c times e to the fundamental solution, right? E to the ta times x naught. So that would be the output if you had no input u. And from that, you can actually gauge how much energy the system produces given an initial condition. Okay, if you compute the energy of the output, that's what I'm doing here, is a lot of work, but I'm computing the energy of the output here, so the integral of y, and if I just use this formulation, I can write it in this form. There's a big matrix here, which I call Q, and x naught are the initial conditions. So this is basically an inner product, and this basically tells me how much energy is produced from this system, if you have an initial condition given. So, so the more energy the state produces, the easier it is to observe it. That's what the idea behind this. So if you have, if this energy is very large, then the initial condition is easy to observe. You could, if you look at this, it's just this is why I have a linear algebra background. If x naught is in a null space or in the kernel of this matrix, which if you look at it is a positive semi-definite at least, then it's not easy to observe, right? If x naught, then this is very small, or if x naught is close to the whole space of this matrix, is in the span of the eigenvectors corresponding to small eigenvalues, then this is very small, and then this state is not easy to observe. Okay, so that is basically observability. So that's related to essentially the second equation here, that's observability. So certain states in the system are not easy to observe. Okay? And you're trying to use this, and so certain states are very easy to observe, and you're trying to use this for your model reduction idea. So that's observability, and then there's another concept, controllability or reachability. Reachability, I like to use it more because it doesn't have the control in there. So what states can be reached, and that basically is defined by the amount of energy that you need by the input to steer a certain initial condition to a certain target. So you have a target given, you have a certain initial condition given, and you want to compute the energy that is required to steer the input to the output. And you can write this in the same way. So you have what input u do you need? So what's the energy u that you need to steer an x naught to a target x of t? So it's basically only considered with the first equation, the state equation. So you can compute this u, the energy. I left out some of the computation here, but it turns out this is another inner product that you get. And P is a similar matrix to this Q matrix, is another semi-positive, semi-definite matrix. Okay, so you've got two concepts. You have states that are easy to observe and states that are easy to reach, and then you've got states that are not so easy to observe and states that are not so easy to reach. It's also a dual concept. And the idea is now, that's also the idea that will turn out to be useful for the stochastic differential equation, is any states that are easy to reach and any states that are easy to observe, you want to make them the same. Okay, so you want to do this basis transformation, remember the V's and the W's. You want to make this transformation so that you have states that are easy to reach and states that are easy to observe are having the same basis. Okay. Please interrupt me if anything not clear. Before I get to that, I have to basically tell you how to compute these Q's and P's. Where's the P here? So you could compute this by computing this integral using quadrature formulas or something. But you can also compute the Q and P by solving Lyapunov equations. So it turns out that P, I can let T go to infinity if A is stable, if A is a stable matrix, and here the same, I can let T go to infinity, so Q and P instead of QT and PT. And these matrices satisfy the Lyapunov equation. It's quite easy to observe by just looking at this integrand and taking derivative with respect to t. Okay, so it's a bit of a little exercise to get the product rule and get A times P plus P times A transpose is minus B times B transpose. So that's a matrix equation. So A is a large matrix, P is a large matrix, and B transpose are usually low rank matrices. BB transpose is a low rank matrix because B is often just a vector. Okay, so this is expensive to solve with Lyapunov equations, but I'm not going to be concerned with that. There are lots of solvers around for doing this, and the idea is to have to do this only once. Right? And this is the same for the observability gradient. These Qs are called observability gradient and controllability gradient. Okay, so if you then have these P and Qs, this is what I said before, I want to compute them in such a way, I want to make sure that any states that are easy, let's start with the difficult one, difficult to reach, are the same as the ones that are difficult to observe. So if you do some transformation that states are difficult to reach, that states are difficult to observe, you do a basis transformation that they're the same, then you can use this for your model.
Can I ask a question?
Yeah.
So it's like you've got a system, and if you hit it on the resonant frequencies of the system, you do well, right?
Yes.
So, but that is it then looking at periodic ones, or could they be exponential solutions? Which of the classes of solutions are you applying it to? Is it complex eigenvalues or real eigenvalues?
The P's and the Q's have their positive definites, so they have real eigenvalues only. But since you have this question, so you could look at the basically there's a relation to the modal, the
right.
Eigenvalues of A.
So are they complex or real? That was my question.
They could be, for A, the eigenvalues could be complex. Yeah. There is, you're referring to a tick. So if there wasn't this output equation, if you have just a state equation, you could do, you could look at the eigenvalues of A and cut off anything that is where the eigenvalues have small absolute value, and cut those off, and then do just a projection of the state equation without being concerned about the output. The thing here is I have an input and an output, and I'm really only interested in the output, which could be a complicated function, but it's just a linear function, but I'm only interested in the output.
Can I ask a silly question?
Yeah,
I don't see how x0 is related to xt. Your equation's on the left, there's no time change. I mean, xt is not related to xt minus 1.
Sorry, I'm a bit
It's
confused.
x of t at time t.
Yes.
But you're saying if I start off with x of 0 equal to x naught, somehow I can reach y of t. But are the x's evolving?
Yeah, there's an x, that's a time derivative on the left, x dot.
Oh,
Yeah,
with
yeah,
respect to time.
This is
okay.
the x by dt. Yeah.
Okay. Thank you.
So this is a fundamental solution, and if x naught is in a certain range, then you might not reach certain outputs. So really, there's a lot of linear algebra going on there. But I hope at least you get the gist. I'm happy to talk to anyone about the details after this. Right, so you have, assuming you have these reachability gradients and observability gradients, they actually turn out to be like covariance matrices. There will be sort of covariance matrices that tell you about the state and the output, covariance about the state and the output for the stochastic system. So these gradients, they tell you how important, how reachable the state is and how observable the state is. And you want to, as I said, you want to have a basis where the reachable and the observable states are the same.
Can I just ask, if you go back to the equation for, I think it's Q, when you're talking about control, maybe the previous slide. Yeah, so how important is the ut equals 0 for that? Because I'm guessing that's just not true in general, so I wonder, I mean, is there a sort of analog for observability when you use some process?
Yeah, that's a good question. So observability is, I have to get back to you on this, but there is an analog for non-zero input. But the observability, this matrix is the same in that case. It's just easier to explain for u equals 0 because I can write down this solution. Yeah, so observability is actually defined in a way that it basically means if you're given an output, can you find the initial condition? If you're given an output in these equations, can you find the initial conditions? It's sort of an inverse problem. Okay. So here is the thing I've been saying a couple of times. So you want to eliminate states that are both difficult to reach and difficult to observe. And so you basically find a basis, you do a transformation and find a basis where both reachable and observable states are the same. So you end up with a linear algebra problem essentially. You have two matrices P and Q, they tell you about observable and reachable states, basically the eigenvectors of P and Q, and you're trying to eliminate the ones that are not important. Okay. Right. So you have your system, you have your gradients P and Q that tell you information about observability and reachability in their eigenvectors. And you solve this Lyapunov equation, you've got P and Q, you've got these matrices, these positive definite matrices. And if the system is called balanced, if P and Q are diagonal, then the system is called balanced. And these diagonal entries are called actually Hankel singular values. So here you've got the relation to the singular value decomposition or principal component analysis. So you basically have you diagonalize two matrices at the same time. So you've got simultaneous diagonalization of two matrices instead of doing just one diagonalization of one matrix, which would just be the singular value decomposition. So you simultaneously diagonalize P and Q in some way, and when they're diagonalized, they are a matrix. They form a matrix which has singular values on the diagonal. In this case, they're called Hankel singular values because it's a slightly different idea from the standard singular value decomposition. So this is basically just like diagonalizing a matrix. You know that a positive definite matrix you can diagonalize, right? So you just U transpose U equals diagonal matrix. Well, you've got two matrices here, and you're trying to diagonalize them simultaneously. You can do this because they're both positive definite. So there's theory, they're both positive definite, so you can do this. And it basically just ends up with a linear algebra problem.
Right, can I ask a stupid question also? But what we're saying then is that there's something very simple then, P is equal to Q, or P transpose is Q. Because then you've only got one thing that's happening. Then these are really singular values.
They're not just singular values, yeah, exactly.
And that's when your output's matching your input in terms of the matrix that's doing the thing. So they're the same thing, are they?
Yeah.
Observability, controllability.
Yes.
Just a quickie, I mean, the simultaneous diagonalability, P and Q need to commute in general. So P commutes, if P Q's QP, then everything should be fine.
Not necessarily. They need to be positive definite.
I'm positive definite. But
They don't need to be. They don't need to commute P and Q.
if you're using orthogonal matrices to do the diagonal. have the same eigenspaces as
Afterwards they will have. So that you have, initially you have a P and Q which is not diagonal, but you're trying to define a transformation such that they're diagonal. Here's actually the transformation of the art. So you can actually do the computation. So you have a P, positive definite. So let's start with that. So P is positive definite. You do a Cholesky factorization or any other factorization like that. You could do an eigenvalue factorization here. So P is positive definite, you can do that. Q is positive definite, you can do that. Let's take Cholesky factorization because that's the easier. P and Q. And then you take the Cholesky factors L and K, multiply them together like this. Do the singular value decomposition. So that comes back to your question: if P and Q are the same, then this is the Hankel singular values are just the singular values. So you do a singular value decomposition, and then you use these transformation matrices T inverses like this. So you take the sigma, the U transpose, and L transpose. This is not so easy to see. You need to get a pen and paper and write half a page. But in that basis, the new P that you get a transformed P and Q because you transform that whole system is diagonal and the same as Q. Okay, this is written out here again. So in this new basis, P tilde, the transformed P and the transformed Q, to get to this is just linear algebra. You transform your A and your B and your C. It turns out your A transformed is that, it's your projection. Well, you're not projecting yet, you're just balancing the system. You do a coordinate transformation. The B and the C, so they're all changed. P and Q changes as well. And in this, if you do this change, P and Q are diagonal and have the Hankel singular values on the diagonal. And they're decreasing as well. So the Hankel singular values are like the singular values are decreasing. Okay, so you've done this transformation, and you now know in this, you haven't actually done anything with the system apart from a basis transformation. It's just a basis transformation of your system. So you have a balanced system, and what you're going to do, you just discard the states which have the small singular values. Because now in your transformed system, your reachable and your observable states are the same. You neglect all the states that are not easily reachable, not easily observable, because they are not interested, and so you do your truncation. So you balance the system, and the next thing you do is your truncation. Okay, so this was sort of a quick introduction to balanced location for deterministic system. I'm going to go to stochastic systems now. Okay, so what I'm interested in is an SDE with added noise. So you have now, so this is where your uncertainty comes in. You have an SDE, but you're actually unsure about the input. Your input has some noise in it. You could model this with the Wiener process, with the Lévy process. I'm going to look at Lévy process, which is just Brownian motion with jumps. And I'm interested in the output. Why? So why would I have a bit of a motivation here? Why would you want to do model reduction for this? To get information. So Y will have error. The uncertainty is propagated through the system. So your output Y will also have error. And you want to measure the error by doing, for example, many solves of this system. So you have an ensemble, and you want to compute maybe the mean of a very complicated function of this output Y. So you need to solve the system many times. Okay, so many times, very expensive. So you want to do a model order reduction. Also, if you want to compute higher order moments of Y, you need to solve the system many times. And the theory that has been developed by the control theorists all rely on something called a transfer function. So do everything in the frequency domain, and that can't be done so easily. The input is noise. You can't just do a Laplace transform of noisy input. Okay, so the way I wanted to explain this is just using one example, and a very simple example. So what I'm going to do, I have a stochastic differential equation, could come from fluid dynamics, wave equations, or heat distribution, as I already said. Discretize it. I'm not going to talk too much about this process, how to discretize it. And then you get a stochastic differential equation, so you're going from PDE to the ODE. This might be very large, and then you do the model reduction. We're going to talk about this mostly, and then you've got the reduced order model. You could go directly do a model reduction from the infinite dimensional system, and people have been working on this for non-stochastic systems, but it's not so clear how to do this for stochastic systems. So this looks more complicated than it actually is. This is just a wave equation, even though last week somebody said this, so it's a boring simple equation. But I used it just to show what's going on. So a wave equation up to here, so without these noisy terms, would just be a standard wave equation, time-dependent wave equation in 1D, damped wave equation. But you get some random excitation using with these noise terms there. I even say what kind of noise it is. So the first noise term is just a Poisson. The first noise term is just the Wiener process, so it's Brownian motion, and the second one is the Lévy process, so it's a combination of those. And you've got Dirichlet boundary conditions and zero initial conditions. And your output, this is an artificial example, your output is, I'm interested in position and the velocity in the middle of this string. It's basically a string, yeah? A 1D wave equation is a string, and I'm interested in the position and the velocity in the middle of a string. I'll just have a little simulation of this, so if that works, because this is now a Windows computer. I haven't tried it. This seems to come up. Yeah, so it's a little bit boring, right? You could think of this as a somewhere where you hang your washing, and it's moving up and down, and there's wind. You're modeling the wind using a stochastic process, for example. So that was the position, and the velocity. The velocity should show you a bit more the stochasticity, because the velocity is not as smooth as the position. Position is an integral of the velocity. So obviously this is exaggerated, but you could think of it as a washing line excited by the wind, which you model for a stochastic process. If I come back to the example that I had earlier with the heat distribution in this room, so you model this with your heat equation, and then you could say, okay, somebody randomly opens the window all the time, and you want to model what the distribution of the heat is in this room, and then you're interested in the heat in a certain area of the room, what a function of the heat distribution in a certain area of the room. Okay, so it's quite a simple equation. Just because it looks so nicely, I've put down the output, the position, and the velocity as a function of time. So then on the left plot is the position, which is smoother than the velocity. The velocity is all these jumps, because it's not an integral of the position. The position is an integral of the velocity, so you get a smooth function. And this I just included because it looks so nice. These are, this is a phase plot, the velocity versus the position. You see all these jumps going on. Okay. So you got a stochastic differential equation. Well, how do I get to the stochastic differential equation? I don't want to go into too much detail, but what you do is you have a second order ODE, you replace it by a first order ODE with a larger dimension, and then you discretize it and you end up with a system like that, a system that I talked about earlier. So we've got almost the same as for the deterministic system, but you have a stochastic input here. And you want to see how this is propagated through the system and what the output looks like. First of all, you need to, the theory tells you for this kind of system, this is your infinite dimensional system, here's your discretized system. You can show that in the mean, the error goes to 0 as n goes to infinity. So if you choose your discretization very, very fine, then your method converges. So you want to have a very fine discretization, but then remember this n is related to the size of a matrix A, so you get convergence in the mean for large n, but n large is very expensive for solving the system. Okay, what you do, you reduce the system using balanced truncation. In this case, but there are other methods as well. So this is not the only method. This is just a method that is sort of related to this observability and reachability idea. Okay, so I've got this system, and what I want to do is reduce this to this system. Okay, so my I basically want to find these gradients again. Observability and controllability gradients. Okay, so my system is written down here. It's almost the same as for the deterministic problem. My solution x not just depends on the time t and the initial condition x naught, it also depends on the stochastic process now. And that's the solution to problem 1, and the solution to the output equation is just the same as 1. And I'm assuming that my matrix A is stable. So all the eigenvalues are on the right half plane. What I was just going to say, the method can be extended to unstable systems as well. But I kept it for stable systems. Okay, and the idea is now basically the same as for the deterministic system. I want to identify states that don't play a big role in equation 1, and states that are not important for equation 2, that don't enter equation 2. And that leaves me with model order reduction for stochastic systems using balanced truncation. It's a lot on this slide, but we've done a lot for this already, right? So I am going to look at the state equation, and I can compute the covariance function of the state x. If I use a 0 initial condition, then I get P of t is just this integral. So it's basically, you solve this system, you compute x transpose, and compute the expected value of it. And you need a bit of Ito calculus to get to this integral formulation. And so this is the covariance matrix of the function x of a state. And it depends, if you look at this, the only difference to the deterministic system is that matrix Q here, which is the covariance of my my stochastic process that I put in. And I can, for stable matrices, I can let t go to infinity, so I get in this case, a Gramian matrix, but it's motivated slightly differently. So you don't do this as I did for the deterministic case. And it turns out any states that are in the image of P are reachable with probability 1. And if they're not in the image of P, they're not reachable. So you've got basically a reachability idea for a stochastic system. So you need to have a probability distribution, probability connected with this. So the probability of if the probability of the state x being in the image of P is 1, then x is reachable. And otherwise it's not reachable.
What does it mean capital T is the final time? Is it possible to be reachable, to be not reachable, then T is big enough it becomes reachable?
If T is...
that T there, the capital T.
Yeah, I should actually, because... What is that? Because this, I let T go to infinity, so this should actually be for all, it should be for all T greater than 0 here. because I let t go to infinity, so this holds for, again, there's a typo there. Okay. And to explain this the idea a little bit better, you can write, so P is a positive definite matrix. You can compute the eigenvectors, little pk, and if you use an orthonormal basis, pk, you can express the coefficients x in this orthonormal basis. You can express the state, your computed state in this orthonormal basis, and these are the coefficients. And the coefficients obviously depend on the stochastic process. Okay, so it's just an expansion in an orthonormal basis, and then you can look at these coefficients. And obviously, because you have a stochastic process in there, you have to look at the expected value to find something. So I'm looking at the expected value of these coefficients, and just by using theory for expected values, I get pk transpose. The expected value of x transpose is my gradient times pk, and that is, because this is a positive definite matrix, is less than equal, and if I increase t, so let t go to infinity, this is less than equal this inner product, and pk are the eigenvectors of p, so lambda k is the corresponding eigenvalue. So if you have a very small eigenvalue corresponding to that state pk, then these coefficients will be in the mean very small. So they don't enter the output state. They're not important. So you neglect them. You would like to neglect them. For the observability, the idea is basically exactly the same as in the deterministic system, because I have no noise on the observables, but I could actually put noise on the observable, which is a more natural thing to do, and then you would have an arrow here as well. But for this talk, I just kept it in the form where you don't have an arrow. And now the idea is actually exactly the same. So I could almost go very quickly through the rest of the slides. You have this is actually a copy of the slide for the deterministic system. You're trying to remove all the states that are not important by diagonalizing, by simultaneously diagonalizing two positive definite matrices. Okay. Here you have to solve the Lyapunov equations, which are slightly different. So the observability, for the observability gradient, the Lyapunov equation is the same as it is in the deterministic case, but for the controllability or reachability, you have a different matrix there. And this is also a slide that I copied from the earlier slide. So you have the same thing that you have to do once you have the P's and the Q's, you do a Cholesky decomposition. You have to do this only once. I mean, these computations are very expensive. You do this once. So you do an offline, you do a lot of work offline, so you can use the reduced system online, where you have to be very quick. So you do this projection, and now we assume we have a system which is balanced. We've got a balanced system, and now comes the truncation. So there's actually a couple of ideas that you can use for the truncation. So that what I'm going to do is I truncate the second line. So I'm going to set x2 equal to, I'm going to truncate the second line and set x2 equal to 0. So I get a system which looks like that, where A tilde is A11, B tilde is B1, and C tilde is C1. So it's quite a simple projection. You just pick the first R by R, the lattice size R entry. There's another idea for a projection which is singular perturbation, which is, I'm not going to go too much in detail about that. So here you just truncate the second equation. But if you take the view that the x2 are the fast variables, so they go to steady state very quickly, you can set the derivative of x2, or the symbolic, this is a symbolic notation because the derivative of stochastic differential equation in that sense doesn't exist, but you set dx2 equals 0, so you get, you set basically the second, the output of the second line, where dx2 equals 0. And if you look at the maths on the second line, you get a slightly different reduced A term. And you have to solve for xt and solve for x1 and plug this in here. Get a you get slightly different A tilde, B tilde, and C tilde. Okay. There's a bit of theory which I don't want to go into because I just wanted to get the idea across. So you want to balance or reduce a system by using reachability and observability and do a common transformation, find a basis where they're both the same. Reachability and reachable and observable states are the same, so that's what the idea is behind this. But you can show when you do this, your reduced system is still stable, both for balanced truncation and singular perturbation, truncation or approximation, so that is fine. What is the error that you do? And again, I'm kind of cheating here. I assume your approximation by a PDE doesn't have an error in it. I'm only doing an error making my reduction. But you can show that in the mean, the error between your solution from the full, your output from the full system and your reduced system is less than equal some a trace, and you've got some constants here. So sigma 2 are the neglected Hankel singular values, which are small, and Ki are some matrices. I'm going to show them, but they look a bit nasty. So these are matrices which involve the matrices that you neglected from your systems and some other matrices that come from your system. So it doesn't really, maybe I shouldn't have even shown them, but there's some constant matrices there. And to get these matrices Ki, you have to solve more Lyapunov and Sylvester equations. But that's just for the error estimate, so you have to work harder for the error estimate. But you can basically show that the most important equation in this slide, you can show that the error in the mean between the full system and the reduced system is small when these Hankel singular values decay very much. Okay, so let's look at the system that I showed you earlier. So that's my damped wave equation. These are some snapshots from the output. Just to remind you what this looked like. And this is the output. So I'm interested in the position and momentum in the middle of the string. Okay, I should have come up with this string. So what this is basically going to show you, this is a system of size 1,000, so it's not very large, okay? But you could easily increase this to 10,000 or 100,000 or more. But what I'd like to show you, you start with a system of size 1,000, and you can, this is the dimension of a reduced system. So the dimension of a reduced system, I go from 64 to 2. But let's just look at 2, so working with 2 by 2 matrices, so that's basically instant and very quick, right? So, so if you have a dimension 2, the actual error for balanced truncation is that size, and this is the error bound. So what you can already see is that the error bound is relatively sharp. Okay. So this is the actual error, and this is the error bound, and this is for the upper approximation. I did this singular perturbation approximation. Again, the error bound is very sharp. So it's the first thing to notice, and that holds for all dimensions. But as I said, even for a reduced dimension of size 2, your error is less than 10 to the minus 1. So you get a really, if you're just interested in doing a quick optimization, these errors are quite small. Even a system of size 64 you could work with, and it's a very small error. So this works really well. And here, just to finish off, I have some plots with the errors. So let's just look at the top one, because that's balanced truncation, what is similar for the singular perturbation approximation. You have here's time, and here's the log of the error, and this error is for the mean. So you compute the mean error over time. So that's quite small. Here I take the reduced system size 6. So this is the error in the first variable, so that's position. And this is the momentum, so you can already see where there is more noise, the error is a bit larger, so the position is the position and the velocity. And the velocity had more noise in the system, so if there's more noise, the error is actually a bit larger. But again, the error is in general over time quite small. So this is the error in position and the error in the velocity. And this is just for one trajectory. It's actually the one trajectory that I showed you initially. So this is the error in the position for one trajectory and in the velocity for one trajectory. So if I now increase the reduced dimension to a larger one, you should get a smaller error. And in do so, the reduced dimension is 24, so the error is even smaller. Okay, so how do you choose the reduced dimension? Well, the idea is you look at the Hankel singular values. So here, and that's a very good thing about this system, the Hankel singular values decrease very rapidly. So this is why it works so well. So if you, this is zoomed in here. So look at the first 100 Hankel singular values. It kind of makes sense to cut off in around here. So 20 Hankel singular values seem to be enough to capture the dynamics of the system, because that's what it's all about. The dynamics of the system is basically can be represented in a much smaller dimension. Okay, just to conclude, so I hope you got a bit of an idea what balanced truncation is for model order reduction, and you've seen that it can be extended to stochastic systems, and I've applied it to the Dant wave equation, but you can do other applications as well. Now, there's a lot of questions coming from this. First one you might have not seen. I actually assumed at some point in the middle of the talk that the initial conditions are all zero. I was cheating there. Because if you have a non-zero initial condition, you need to do your reduction so it also captures the initial condition. And I haven't done this, but it can be done. It can be done for deterministic systems. Problems are, what do you about nonlinear problems? What to do about parameter-dependent problems. So if you think about, for example, have A, let's look at the system A being a parameter-dependent PDE, for example, with the parameter being uncertain, you could do something similar, but you obviously have to do something to the matrix A to do this, to the reduction properly. Yeah, so I hope you got some idea of what I've been doing. Thank you very much.
Any further questions? Just a quickie. Your UT, that's it's a sensible question. The UT, is that a control? Can you, for example, if you're doing system identification, can you change the UT in order for you to be able to identify the system better?
Yes, yeah, that's what the people in control do. They control UT to be able to get
It's sort of
this,
called persistent excitation or something. You excite the system so that you observe, and then you observe the Y, and then it helps you identify.
yes.
And does your theory have a bearing on that? I mean, if it's controllable and reachable, then that helps you. If you put an input control, so it's controllable, that helps you identify. Is that a minimum?
Yeah, that's what basically the A, B, and C matrices basically are sufficient to be able to say if this system is controllable or observable. So the U, even though you can treat that U, is not really influencing the controllability of the system.
So your A is symmetric positive definite here, right?
Not the A. The A is just it's stable. So the eigenvalues have to be in the right half plane.
Well, then I want to get back to Henry's comment, because it's absolutely true that two matrices are simultaneously diagonalizable if and only if they commute. That's a true statement. So there's something about the duality of observability and controllability that saves the day here. Because, yeah, it's true. What Henry said is true.
Thank you for that. A lot of different people saying that.
If and only if and only if state.
Okay.
Look it up. No, I mean, I think it's okay because I think the duality between, there's a duality between observability
Yes, yes.
and controllability. I
Yes.
think that's
Yeah, yeah, yeah.
that's why it works in this case.
Yeah.
And the reason I asked about positive definite, I'm symmetric. I wasn't sure if that duality holds for general A or not. But I don't know that. It must.
Well, the A doesn't have to be positive.
Yeah, no,
definite,
but I
it's
mean,
symmetrical. The P's and the Q's.
I don't know if the A, if this how this duality works. For positive definite, I believe it. You know, I can see that it's true. But
It's
it may
actually
be true in
sufficient if
general.
one of them is positive semi-definite, it still works. If
Which
one of
is-
the P's or the Q's is positive semi-definite. It's basically like
If and only if they commute. I mean, don't take my word for it. Go look it up.
So I actually just looked it up, and there's an extra condition. So it's not if and only if. So it's true that if they are simultaneously diagonizable, then they commute. But if they commute, then you have to have an extra condition that there are no multiple eigenvalues.
Yeah, but that doesn't. So that's an extra condition.
Yeah, so it's not in if
for the other direction.
Well, but then that's a very special condition, right?
We should maybe discuss this outside.
Yeah.
Very nice hearing.
Any other question?
Very nice.
Fantastic.
So P is a dense matrix, right? Q as well.
Yes.
Yeah. So then there must be something that you didn't talk about here, because if you have PDE, you have like really 10 to the not 1,000, but like 10 to the 6 number of degrees of freedom. You're not able to even store that matrix.
Yes, yeah, that's what I neglected. I basically said, where's my Lyapunov equation? I basically said, okay, I can solve this Lyapunov equation without a problem, but that's, where's the Lyapunov equation? It was somewhere. Yeah, it's here. So you've got this, A is massive,
Yeah.
often sparse.
Sparse.
B is often, the right-hand side is often low rank. What I didn't say, yeah, if you want to solve this Lyapunov, I basically said I can solve the Lyapunov equation, everything fine. The P, it turns out the Lyapunov equation is not solved as you would maybe solve it. It's solved using a low rank solver. So it turns actually out in this kind of structure that the P has a low rank. So you only ever you store P in low rank factors. So P is Li transpose, and Li is a long thin matrix. So it's, yeah, you're right. It's there is a cheating there. Basically assume that this is done quickly. So you already have these low rank factors. You don't even do Cholesky factorization. You have these low rank factors given. Yeah.
But that's sort of an additional assumption on the PDE system, right? There might be, or might there be systems where this is not the case?
If you have a stable system and a low rank right hand side, yeah, there are systems where it's not the case. Yeah, you're right. But if you have a stable system and a low rank right hand side, and A has some sort of sparsity structure, then you can show that the solution has low rank. But there are lots of cases where it's observed practically where the solution has low rank, but it hasn't been proved.
But the important part is that B sort of is low rank. So what you
Yeah.
how you actually perturb the system and how you observe the system, this is finite dimensional quantity, low dimensional quantity.
So if B is not, if B is full rank, the right hand side is full rank, then you have examples where P is not low rank. And yeah, so it works for very special particular systems very well. But there are other methods, not balanced truncation, there are other reduction methods where you don't have to solve the Lyapunov equation. that's one of the sort of bad things about balanced truncation. Solving this Lyapunov equation is expensive in general.
So I've got a sort of clarification question. I was just wondering about your error bound. Is that for going from the ODE to the reduced order ODE, or from the PDE to the reduced order ODE?
From the ODE. So you have from the out from the ODE. So I've discretized the system, and I'm looking at the error in the output. So the error in the output. It assumes you've discretized the ODE, the PDE already. So you get an ODE for the time-dependent system, and then you look at the error in the output. So there are several error steps that you do in between that I basically reject.
But that step's controllable. Going from the PD to the OD, you can control the error in that step.
There's
It makes no
basically-
sense to make this thing any larger than that error you've already committed.
So there's basically, if you want to do this, if you want to, you could basically look at the infinite dimensional system and then do the reduction, go straight from there. Or you do these several steps. And each time you do a step, you do an error. As you do an error right at the beginning, when you formulate a PDE for your system, for your physical system. But there is the sort of, coming back to sort of the program, there's no reason why I've never really thought about this in detail, how you can apply this to a system that doesn't come from a physical system. I mean, can you do this reduction process when you have a system which comes from the system where you just have the data? You reduce the data, you could reduce the data. But a system which doesn't come from a physical system, there should be something that you may be able to do.